if we look at our formula, I can plug any numbers in for x and y, because we're just, in the numerator, we're just multiplying by x and y, so there's no algebra rules that are stopping any particular value from x or y being plugged in. E can be raised to any number that we want, and e to a power will never equal 0. So e to, whatever the power ends up being will never be 0. So I will never be dividing by 0. Hence, just as a function itself, all numbers can be plugged in. But now that we are not just in 2 dimensions, we actually are in 3 dimensions, we're not going to say all real numbers for our domain. Instead, we have to make sure that we're explaining that it's all real numbers for x and all real numbers for y. In terms of these multi-dimension functions, it's actually clearer to explain graphically or geometrically if you can. So I think the best answer for the domain is to write the xy plane. You're explaining that any point in the xy plane could be used as an input. It's still the same information if I put x as an element of all real numbers, y is an element of all real numbers. You could also state it this way. There's nothing incorrect about that. But I'm just saying in the big picture, if you're trying to imagine your surfaces, I think it's more helpful to kind of identify what geometrically you're actually able to use. So that this surface could spread out over the whole xy plane. This particular function does have a restricted range. The tops of the mountains do top out somewhere, and the valleys also bottom out somewhere. So you can kind of see from the graph here that the valleys don't get any lower than -1 something, and they don't get any higher than 1 something. And so I do have a restricted range. Finding it takes a little bit of algebra finessing. I mean, basically, I kind of stated it on your paper. It's written there from -1.16 to +1.16. The 1.16 is a rounded off value. So what I did is I kind of started with the graph, and I could tell, it's from -1 something to +1 something, and then I played with plugging in numbers to kind of figure out, well, what am I going to do to, reach the bottom and reach the top. I will admit that's what I did when I was putting this together. In a later section, we are going to go over how to locate minimums and maximums of surfaces. And so the methods of that section would allow us to pinpoint it exactly. And so after I kind of just plugged in numbers and played with it, I did double check it with those methods. But I don't want to get into those methods yet because we're going to do them in section 14.5. But my point is, our range is not all real numbers, and it's a segment of the z-axis. So my domain is 2-dimensional, but my range is 1-dimensional for this function. And so z is between -1.16 and +1.16. All right, so that's just one of the other concepts I want you to pay attention to, that my domain is 2-dimensional and my range is 1-dimensional. The range is actually part of the z-axis. The domain is the whole xy plane. All right. Other aspects of studying 3D functions are going to be to think about the derivatives of the function. We are now in multiple dimensions. So what does it mean to find the derivative? in Calculus 1, when we were studying two-dimensional functions, where I plug in one input, I get out one output, the derivative was the instantaneous slope. It was the slope at any particular point. Well, look at our surface. Our surface certainly has slopes. It has slopes in all kinds of directions. We will, as we go through the whole chapter, talk about how to find the slope in any direction, but tonight we're just going to start with the idea of finding the slope just in the x direction, or finding the slope just in the y direction. The way the picture's oriented right now, this is y, and so you can kind of see if I found the slope right here, I would be finding the slope in the y direction. So the notation for that is this. You also will see dz, dy, okay, the derivative of z with respect to y. There's also this other notation where we would write something like that down, and this is not a Greek letter. It's some symbol that's kind of been made up. It looks kind of like a Greek letter, but it's not really a Greek letter. And this is read the partial derivative of z with respect to y is how this is read. So this symbol has the name the partial. If you write that symbol down, you're going to hear somebody say the partial derivative of z with respect to y. But all of these mean the same thing, and so notation really should just be about communicating. I'm not going to be a real stickler about whether or not you're using partial or whether you're using the d that you're already used to. If you write this down, I know what you're talking about. You're finding the derivative, you're finding the slope, the rate of change of z with respect to y. And what does that mean? It means if I slice the curve directly down the y-axis, I'm saying directly down the y-axis because it kind of helps you picture it, but really if any plane parallel to the y-axis. So picture slicing this, so slice surface with any plane parallel to the y-axis. If it's parallel to the y-axis, then it's parallel to the xz plane. Okay, because you're chopping y. And you are then finding the slope on the curve created by the slice. Okay, and on your packet, I do kind of have a drawing of that. I'll bring up the packet in a moment. But I wonder if on here I could graph implicit, and I just, let's see, I want to put in the plane that goes through y, so that would be x equals 0. Let's see what this graph is like there. Yeah, there we go. Is that? Okay, I graph the plane x equals 0, and if I graph x equals 0, it chops it right down the y-axis. And if I type x equals 0, then I'm restricting x to be 0, y and z can be anything. So actually, wait a minute. Sorry, I guess this is the y z.
That's what I was wondering.
My plane is made up of y and z. So, anyway, if you slice it, you can kind of see that you're creating this curve, and the derivative of z with respect to y is the slope at any particular, you pick a point, and if you find this expression, you can plug that point in, and it's giving you the slope at that point along that curve. So again, on your packet, I made similar planes. If I type y equals 0, then I'm slicing it down the x-axis. There we go. Okay, so again, I've sliced it. Here's my x-axis. I've now graphed y equals 0. So where I've sliced it is creating this curve. And so if I find f sub x, which is dz dx, or the partial of z with respect to x, I'm finding the slope at some point on that curve. All right, so why don't we practice with the one that we have, okay? So first in your packet, we're being asked to find f sub x. And so if we're being asked to find f sub x, it means that we are slicing it along the x-axis, creating a curve, and we're finding an expression that would allow us to get the slope at some point on that curve where we've sliced it. When you find a partial derivative, you treat the variable that you're taking the derivative with respect to as a variable, but all the other variables get treated as if they're constants, as if they're 5 or 2 or, you know, whatever. Was this positive 0.5x squared plus 0.8y squared? All right, so here's my original function. I'm taking the derivative with respect to x, and technically it's a 2D function, so we're still, when we get the derivative, we'll still plug in x's and y's, but I'm going to treat y as if it's a constant. I'm treating x as the variable. So doing the quotient rule, I have denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. I'll get out of the way in a second. And why don't I mute okay, so denominator, derivative of the numerator, minus the numerator, times the derivative of the denominator, divided by denominator squared. And if I, well, I'll start that first. Okay, so let's kind of talk through this again. I'm doing the quotient rule like we learned in Calculus 1. Here's my denominator, as is. The numerator is a linear function in terms of x. X is being multiplied by 4, and the constant y. We're treating y like it's a constant. So 4 times y is like the slope of the numerator. So 4y is the derivative of the numerator. And then minus the numerator times the derivative of the denominator. Remember, derivative of e is itself. So that's why I rewrote e to the 0.5x squared plus 0.8y squared. But then the derivative of this with respect to x, I'm going to do the power rule here. So 0.5 times 2 will be 1, x to the first power. This is a constant. So when I take the derivative of that, I just treat it like it's a constant, and so the derivative of constant is 0. In terms of cleaning this up, I could factor out 4y e to the 0.5x squared plus 0.8y squared, and I would be left with 1 minus x squared And you know what, since I'm squaring the denominator, this cancels one of those.